Okay, thank you very much for the introduction, actually. Okay, so yeah, I'm going to talk about this joint piece of work that I've done with my supervisor, Professor Alex Beskos. And the topic is particle-based inference for continuous discrete state space models. If the slides will move forward. Um, oh, okay. Okay, something seems to have activated, so let's go with that. Okay, so I'm going to start off by introducing the class of models that we're going to be working with. So the class of models is the continuous discrete state space model, and we start by defining this process by defining a continuous time latent process that's driven by a stochastic differential equation. Now, from a modeling context, the reason why we might want to use a stochastic differential equation to model a latent state is we might have some kind of dynamical system that we believe evolves via some kind of ODE dynamics, and we might have some understanding that we can embed into the drift on how these states relate to each other. Now, the stochastic differential equation then extends that by introducing an element of randomness into that process. So by using an SDE, we can correctly quantify our uncertainty regarding the latent process. Okay, so the observations, so we have capital T observations. One thing to just note as I go through is that S throughout will be used to denote continuous time, and lowercase and uppercase t are the discrete time observations. Okay, so we have some observation model F, and this can be very general. There are no real conditions on this. This can be nonlinear, it can be non-Gaussian. We just need to have access to the density. And we have low frequency observations. So I'm going to discuss a bit more what exactly I mean by that shortly. And before I go to the next slide, so the goal of this work really, and the inference objective, is to find the continuous path of the process given the observations. So immediately we're thinking about a Bayesian inference problem. We're going to immediately go to tools of Bayesian computation. So the first thing we're thinking about is Markov chain Monte Carlo, or the topic of this work, which is particle-based methods or sequential Monte Carlo methods. Okay, so here's a concrete example of this particular model class. So this is a Fitzhugh-Naguno model, which is used to model the action potential of a neuron. So this first component is the action potential. The second component is the conductance dynamics. And the observation density is only in the action potential, which is common in application. And I said earlier that I would discuss what I meant when I was describing a low frequency setting. So when I say low frequency, I don't mean in terms of absolute value. So you can see here that the value here is 0.05 milliseconds, which we would think to be quite small in absolute value. I'm talking about the degree of non-linearity that exists in between the observation times. So here is a visualization where I just zoom in between these two observations, and we can see that the process is highly non-linear. Okay, so we're going to talk about inference in this class of models via particle-based methods. So in more recent times, particle-based methods have been applied for general Bayesian computation, in particular when we have posteriors with multimodality. These particle-based methods are also applied for rare event sampling, and in more recent times, we've seen them applied to guiding in the context of generative modeling via denoising diffusion models. But this class of inference methods, when they originally came about, they were about doing inference in state space models, which is a particular Bayesian model where the prior is defined via a Markov process. So it seems like quite a natural approach that we should then model this class, the continuous discrete state space model, as an extension of the state space model using these methods. So the focus of this talk is going to be, I'm going to talk a lot about this particular inference problem, offline smoothing, but we're also going to talk about, this is going to be the main topic of this talk, but what we're really going to develop and what this contribution is about is a framework for inference in this class of models via particle-based methods, and that could involve not just this inferential objective, but some others as well. So we could talk about filtering or prediction, online parameter estimation. And yeah, this is the contribution. Okay, so what challenges do we associate with particle-based methods in this class of models? So the first one involves the use of proposals. So when we're working with particle filters, the way they tend to work is we simulate particles from some kind of process, some kind of proposal. Usually this is the signal process by default. And then we apply some weights to each of these particles. And upon applying these weights, we've essentially reweighted these particles so they now represent the target distribution of interest. Now, to maintain performance of these methods in higher dimensions, we need to make sure that we somehow guide these proposals. So we need to come up with proposals that take the observation data into account. And that way, when we're applying these weights, we're not moving as far from one distribution to another. Unfortunately, in the continuous discrete context, we can't do this because the weights involve the signal transition density, and this is typically intractable. And as I said, these proposal mechanisms are essential for performance in higher dimension of the latent state D. So the solution that we consider is data augmentation. So instead of considering point proposals, i.e. proposals of particles that are on the reals, we instead consider a full continuous time path proposal in between the observation times. And using these path proposals, we can then condition on Y. Okay, so the second part is to do with path transformations. So the problem itself is that many particle-based algorithms involve ancestor resampling steps. So what these ancestor resampling steps do is they carefully change the ancestors after the particles have been sampled in the particle filter. And these are very well known theoretically and empirically to improve performance of particle-based methods for large capital T, i.e. the length of the data. However, these updates are degenerate for this class of models when the particles are defined as continuous time paths. And really the main thrust and contribution of this work is that we carefully define path transforms of the latent signal that break this degeneracy and enable us to update the particle ancestors. Okay, so to be honest, I think with this particular degeneracy, I think a picture paints 1,000 words, and it's very hard for me to describe without having something like this. So I'm going to talk through a particular algorithm that updates ancestors in a backward pass so that you're aware of why this degeneracy occurs and why a path transform might be the solution to this problem. Okay, so as I mentioned earlier, we have path proposals and we're calculating weights associated with those proposals. So in this example here, so let's start from st minus 1 up to st, okay? So we simulate 3 particles. This is our first step, and then we apply weights. You can see that the paths that have bigger weights are closer to the observation because they're more representative. And then we have a resampling step. In the resampling step, we see that the ancestors of these 2 particles, they do have some ancestors that then go on to the next time step. But this particle here is not very representative. So in the resampling step, no particles are recovered. Now, in a forward filtering backward smoothing algorithm, we might have this particle P1 T plus 1 that is our representative of the smoothing distribution. And then how this algorithm works is it then wants to potentially select a different ancestor to its existing one to represent the smoothing distribution. So this particle PT2 could be a nice ancestor for PT plus 1, 1, but we actually can't select it because the endpoint of this path is not equal to the start of this path. So this is essentially the reason for the degeneracy, because if we were to select that particle, then we would be saying that the path is discontinuous, which is impossible for a continuous time process. So the way that we resolve this problem is we implement this transform, and instead we simulate the particles on this space instead. So as we will see later, the way this decomposition works is we simulate the endpoint of the path, and we also simulate some driving noise, and we have a function that is essentially the proposal for a diffusion bridge that we can use to connect the start points and the endpoints in order to evaluate these potential weights that we then use to resample the ancestors. Okay, so I've now introduced the problem. I've said what the model is that we're working with, and I've said what the contribution is. So next up, I'm going to discuss what these path proposals look like that I mentioned that we need to use in order to maintain performance for higher dimensions of the latent state. I will then discuss these path transforms. We have 2 types, forward and backward. that are essential for ancestor resampling, which is essential for performance with the length of the data. I will then empirically demonstrate what we've come up with, and then I will present some concluding remarks. Okay, so I mentioned earlier that we have two different path transformations, and corresponding to that, we have two different sets of path proposals that are compatible with them. Now, I'm going to discuss why we came up with two of them and what the advantages and disadvantages are of both. So for these forward ones, we have more flexibility in the choice of path proposal, i.e. it's easier to come up with something that takes the observation into account. The bootstrap proposal is a special case of this type of proposal for the forward, but we can only use this construct when we have elliptic SDEs, i.e. that the diffusion coefficient is invertible. So in this backward construction, we have less flexibility in the path proposal. The bootstrap is not a special case, but we can relax this invertibility condition, which means that we can do these backward smoothing algorithms on hypo-elliptic diffusions. And many interesting applications that involve this class of models do work with this hypo-elliptic class. So another thing that I might note that's quite interesting is that, so it might seem quite funny to people that are a bit more familiar with particle-based methods, but it turns out that in order to do this backward sampling, as far as we're aware with these constructions, you actually have to introduce a proposal into the filtering steps in order to do particle-based smoothing, if we have a hypo-elliptic diffusion with this class model. Okay, so now I'm going to discuss, okay, what does this forward proposal look like? This is one of our choices. So this is the more flexible one. Okay, so it looks like this. We have a lot of flexibility. So we just need, the only conditions we really need on it is that the diffusion coefficient matches that of the signal process. And then we can choose our path proposal to be whatever we would like it to be. We would like to use information in the data when we're choosing our drift function so that we can push our path to be closer to the observation. So we have this optimality result that we can use to help us actually pick something in practice. So we can show via Doo's H transform that we have a situation where we can minimize the local variance of our weights in our path value particle filter if we use this choice of drift function, which involves this score term, which involves this rho function, and this rho function involves the transition density of the signal process, and therefore we don't actually have access to this thing. So we can't take the optimal thing in general, but we can replace it with something that we think is close to it. So we replace it with this tilde thing. And what this thing actually represents is we replace the transition density of the signal process, which we don't have, in this rho function with the transition density of a linear SDE. And for a linear SDE, we do actually have this thing. Okay, so that's one of our constructions, which would probably be the first thing you think of when you try to come up with a path proposal, just simulate a path. But this one is slightly different, and it turns out that it's useful for this backward smoothing stuff, which is not necessarily intuitive when you first look at it. So the idea is that instead of simulating a path, we first simulate the endpoint of the path, and then we connect the start and the endpoint with a diffusion bridge. And I said earlier that in this class of the backward ones, we have less flexibility in the proposals in terms of coming up with something that is performant. And I'll just give you a bit of intuition as to why that is the case. So when we're trying to come up with some kind of distribution with which to define the ending point, this is quite tough if we have high degrees of nonlinearity in between those observation times. You know, we don't really know if there's a lot of nonlinearity. If we want to just define some density that could be our endpoint, this is quite tough. One thing to note is that, yeah, so these can be more performant under low observation noise. So if we have a Y that is very close to the signal process, and this gives us a lot of information about where the point ends, then yeah, of course, we can embed it into this guy, and that can help us with performance. So then the next step is to come up with some kind of diffusion bridge proposal, because the true diffusion bridge is in general intractable. And we use similar ideas to what I mentioned earlier. So the diffusion bridge involves a drift function. This drift function involves a term that involves the transition density. We replace that transition density with the transition density of a linear SDE. This gives us a formally defined proposal. One thing I will note is that this isn't our stuff, this guided bridge proposal. This is something that we just take and use in our framework.
The question was that rho said it was unavailable.
Yep.
Is it unavailable because you don't know what the parameters are, or is it unavailable for another reason?
Um,
Not unavailable.
So
something, or what
the rho, so I haven't properly defined the rho, but it involves, so it's the integral of the transition density multiplied by the observation density. And the transition density is the transition density of the signal process. And because we consider general classes of signal processes, we can't guarantee that we have this. So it's something that we know that this is the function that is involved in the drift, but we don't have it. So we replace it with something that we think is close to it.
It's intractable.
Yeah, it's intractable. Yeah.
Does it depend on y too?
Yes, it does. Yes. That's right. That's an omission. Yeah. So this does depend on the observation. Yeah. Yeah. So it's the transition density multiplied by the observation density, and then we take the integral.
So it's not that you don't have it. It's just that you don't have it.
Yeah. Yeah. I mean, we can't.
You don't want to count. You don't want to do a math with it, but you have it, right?
It's the integral of something, and then something inside the integral we don't have. So.
It's not a big support. Yeah, but it's not like I don't know the key for a point I don't have. It's not like some distance parameters, right? This.
Okay. Okay, so I've defined these two types of path proposal. Okay, so I have forward proposals and backward proposals that mean that we gain some kind of performance for a large dimension of a latent state. Okay. Okay, so the last thing I'm going to go through now is what these path transforms look like. Okay, so I have forward transforms and backward transforms that guarantee performance when we have more data. So this means that when we change these particle ancestors, we use algorithms that change particle ancestors, and these will be performant when the data is large. Okay, so I have omitted technical details here just to give intuition for what these transforms are doing. But let me give you some idea of what's going on here. So we just defined two types of proposal kernel on this X space. So we had a forward one and a backward one. And now I'm going to define two alternative ones on the Z space. And what this Z space is going to involve is we have a path and we have an ending point that comes from the distributions I defined earlier. And we're going to keep the endpoint where it is, and we're going to apply some transform to the involved path. Okay, so what are the key properties of these transforms? One is that we can simulate from the kernel. We need this because we're going to be using it in particle filters. So we need to be able to simulate from these transformed kernels. Another property that's important from the perspective of being able to conduct ancestral resampling is having a density that we can evaluate with respect to some dominating measure. And this dominating measure cannot depend on the endpoint of the previous path. This is the crucial aspect. And we're on the path space, and it turns out that we work with the product measure of the Wiener measure and the Lebesgue measure of dimension D. And we show this is the case. From the Z space through some map. So we need to be able to take our corresponding transformed kernels on the Z space and apply some map to get them to the X space. And we need to be able to access this map so we can actually do this, so that we can calculate the ancestor weights. Okay, so I'm now going to explain how we actually define the transformed kernel. And I'm going to give a bit of intuition. So you will recall that I mentioned that under the backward transform, we are able to, under the backward transform, we are able to do particle-based smoothing for hypo-elliptic diffusions, whereas this is not the case when we have an elliptic diffusion. So I'm now just going to discuss briefly why this is the case. So what does our proposal distribution now look like under the transform space? So what we do for this particular one is we just simulate according to the Wiener process a path, and then we take this proposal distribution for the ending point that I mentioned earlier that we previously defined. And now I'm just going to talk about these three properties that I said we need to have of these reparameterized kernels. I'm going to go through them individually and explain for this particular case why it is that they are satisfied. Okay, so the first one is that can we simulate from the kernel? And the answer is yes. So it's the Wiener measure and this thing that we previously defined. Does it have a density that we can evaluate with respect to the Wiener measure and the Lebesgue measure of dimension D? Yes, it does. It's just this guy here. Okay, it's just this M. And then the final condition is, can the kernel on the X space be recovered from the kernel on the Z space through a map that's needed to calculate ancestor weights? And the answer is yes. So this H is defined as the map from the Brownian motion to the solution of the proposal bridge that we defined in this backward construction. So if we apply this map to this kernel, then we will recover this kernel. And when we apply this map, we fix the ending point. So we leave the ending point alone, and we're only transforming the path that's in between the observations. Okay, so one thing I'm going to mention now about the hypo-elliptic stuff is, okay, so why is it the case that we only need to be working with a hypo-elliptic, or we can work with a hypo-elliptic diffusion and use this transform? And the key idea really is that we don't need a map from the X space to the Z space in the context of this particular transform. Okay, so now I'm going to discuss the other construction. So the second construction is the forward transform. And this is the one that has more flexibility, but is limited in its application in the sense that we can only work with elliptic diffusions. Okay, so in order to describe this, the mathematical object here, I think the easiest way to describe it is to talk about, okay, how do we simulate it, okay? And it's a slightly tricky one to get your head around, I think. So we start off by simulating this path proposal that we earlier defined. So we simulate this path proposal, and then we keep the endpoint fixed, okay? Now we fix this endpoint, and then we can define, we can take a choice of diffusion bridge proposal. It doesn't matter really what we pick, but whatever we pick, we can achieve this transform that allows us to change particle ancestors. And we can take this thing and we can apply the inverse transform of this proposal bridge from the X space to the Z space, i.e. a transform from the solution of the diffusion bridge proposal back to the Brownian motion. And if we apply that transform to this thing, then this is the distribution that is recovered from that simulation process. So that's how we simulate from this kernel. And in that explanation is essentially the key to why it's the case that this particular transform cannot be applied in the case of hypo-elliptic diffusions. So one of the key conditions is because we're going to use this transformed kernel to simulate particles, we need to be able to simulate from this star. And basically that means we need this inverse transform from a solution of a proposal bridge to the Brownian motion. And this requires invertibility of the diffusion coefficient. So this ft minus 1 here is this map from the solution is the map from the solution of a proposal for a diffusion bridge back to the Brownian motion. And this essentially involves taking the inverse of the diffusion coefficient. So I haven't given full exposition of why precisely it's the case that under this transform, these three properties I had in the previous slide are satisfied. But what I really wanted to communicate is what the key differences are between the two transforms. So you know, okay, when do I use one and when do I use the other? And to hopefully provide some intuition as to why this occurs, that we can only use elliptic diffusions with the forward, and we can use hypo-elliptic diffusions with the backward.
Sorry, the way it's written, it's a bit confusing.
Okay.
Say on the left, fixed x of st, and then you set the z is the f inverse. But one of the arguments of the f inverse, ft inverse.
Sorry, this should be x. Yeah, that should be x.
Okay.
Yes. Yeah.
Okay. Because otherwise, it'd be very easy to.
Yeah. That is true. That's true. Okay. Okay, so we're whizzing ahead. I think we're going to finish a bit ahead of time.
What's non-invertible? Some diffusion of
The diffusion coefficient. So if I go all the way, oh, it's not letting me go back behind there. But basically, it's the diffusion coefficient is this guy. Didn't know do that. I think I know how. Okay. Yeah, it's so the diffusion coefficient is this sigma, and that defines how much noise is injected into the process as it evolves through time. So standard choices for X, sometimes people take it to be constants, or they take it to be some kind of multiplicative thing where it depends on the magnitude of X. Does that answer your question?
So non-invertible in the sense that like for instance, I can't invert the CDF to normal
or? In the sense that if you plug in some value of X, you recover this guy, right? And then dW needs to be equal to D. It's one thing. So that's the dimension of the Brownian motion. And then in order to have invertibility, then you've got some function that evaluates to a D by D matrix, and we're talking about the invertibility of that matrix.
Oh.
Does that make sense?
Yes.
Okay.
Nothing not invertible.
So elliptic means it is invertible.
And hypo one is not.
Hypo-elliptic is non-invertible. Yeah, that's right.
So for all excess.
It is, yes. So for all values of so the XS is the actual random signal process itself, but connected to that is a sigma, which is a function.
So the function for every value of the argument excess.
Yes. So for every value of X, it's invertible. Yeah. Okay. Any more questions as I'm just flicking through to get back to where I was? Look. Okay. Please do something. Oh, spoilers. Don't want any spoilers, do we? Okay. So now let's get to the practical implementation. And to be honest, I haven't gone in very hard on the numerics, and the reason why is because these transforms, as soon as we formally define them on the path space, they give us access to existing algorithms, and we already know that these existing algorithms perform better than inferior particle-based methods that do not change ancestors. Okay, so again, we go back to this particle model, and we're going to implement a particle MCMC method, which is called iterated conditional sequential Monte Carlo. And the idea behind these particle MCMC methods is that we come up with some kind of proposal for the full latent state, which is in this case a latent path. And the way we construct those proposals is by using particle filters as proposals. Okay, so particle filters are involved to come up with the proposals, and we have these three different choices. So you might recall, if I go back a few slides. You might recall earlier I mentioned that, so we have a hypo-elliptic diffusion, that's the first thing. So if we look at the definition of the Fitzhugh-Nagumo model, it is a hypo-elliptic diffusion. So we're in this setting. So if we want to implement these backward sampling steps that improve performance, we can't use the bootstrap. So we actually have to use a proposal in order to use the backward sampling steps. So with that in mind, I think the resolution of this plot is too big. Yeah, so with that in mind, we run three algorithms. So we run the bootstrap particle filter as the proposal mechanism within the MCMC chain. We run this, we come up with a backward proposal, but as I defined earlier, and we introduce this, and then we run the algorithm both without and with the backward step. So we have this option of whether or not we use the ancestor resampling step. So this is a demonstration where we can quite clearly see the impact of implementing this on the performance. Okay, so these are the results. So we run 8 chains, each for 1,000 iterations. We use 50 particles in each of the particle filters. And we actually have to, because we're simulating paths in between observations of particles, we actually have to simulate imputed points, okay? So these are just the algorithm settings. And if you see, if you look at any SMC papers on these algorithms, it's very common that you see plots that look a bit like this, basically. So the green and the red line, these algorithms don't have this ancestor resampling step involved. So there's path degeneracy. And what we get is basically the chain is not updating beyond this point. So this is a quite clear example of what happens to the performance of the algorithms for longer time series. And this is an example where I think T is only 100 in this example. And then you can see that because of the ancestor resampling steps in the blue line, that thankfully we overcome path degeneracy, and we're getting a good representation of our posterior distribution across the entire time period. Okay, so we're getting there. So the last one is concluding remarks. Okay, so I'm just going to remind you guys everything I've been through. So particle-based methods that resample ancestors that result in methods scale well with the length of the data previously could not be implemented for the class of continuous discrete state-space models. And our solution is that we can carefully define two path transformations that we formally define in the path space that enable the application of these methods to the model class. The transformations are compatible with path proposals in the filtering steps, which are essential for performance. We increase the dimension of the latent state. And now this is kind of what I'm trying to do now, which is we think we can extend these approaches to other classes of continuous discrete state space model, where instead of having, so one way to model the continuous time process is as a diffusion process, but we could also consider maybe jump diffusion processes or pure jump or Markov jump processes. And then the final thing is that to demonstrate the applicability of these transforms that we've developed to a broad class of SMC algorithms, what we've also done is we've embedded the path transform framework into the particles package. So the particles package was developed by Nicolas Chopin, and it came with his introductory book on the topic of SMC, An Introduction to Sequential Monte Carlo. And the idea behind this package is that we can use what's called the Feynman-Kac model, which is basically just a statement of what the proposals on the weight side in particle filters. We can use this as an abstraction inside the code, and then we can use this abstraction to implement any SMC algorithm. So this kind of goes towards the theme of the generalizability of these transforms. And yeah, so basically I've extended the software, and it's defined, it's constructed in a similar object-oriented way. So in the particles package, we define a state space model as an object. And then given that state space model, we choose our Feynman-Kac model, which is basically us choosing our proposals. And then finally, we define an algorithm to implement on that Feynman-Kac model. And I've basically done something similar. So the first step in this framework is we define a signal process, which is the SDE. Here I've just used a simple Ornstein-Uhlenbeck. And then in the next step, we define a continuous discrete state space model. And by doing this, we basically just need to define the observation density. And we also need to define, okay, what are my spacings in between my observation times? Okay, given that, we can then define a Feynman-Kac model. And the Feynman-Kac model is essentially where this stuff I've been talking about comes in, because this is where we specify what the proposals and the weights are. And I've got this automatic thing set up where you can just write from here, import backward or something like this. And then you can use the path transformations that change the ancestors without having to know the gory details about how to actually construct the path transforms. They're already implemented in there so that you can kind of treat it as an abstraction barrier and you can immediately get towards using them. Okay, and then the final step is choose whatever algorithm you want off the shelf of particle-based methods and implement it. So here I've just used the particle filter, but other options are available. Okay, so we did it. Thank you very much.
Thanks very much, Chris. I think we've got 10 minutes for Q&A. Yes, yeah.
Thank you very much. Super cool that you did into the particles package as well. In that sense, do you have an intuition as to if I'm in a situation where either forward or backward transform is possible? Do you have any intuition as to which one should be preferable?
I would probably lean towards the argument I made about the proposals. So I would maybe say, so basically, so if you can use both, which would be in, say you have an elliptic diffusion, then you could use both. This is the one that takes some time, I think. Okay. Yeah, so let's look at the proposals. Yeah, so one thing I basically discovered when I was doing the numerical experiments is this thing, which is that, so the backward proposal, if you're not careful enough, it's necessary in the hypo-elliptic case to actually do the ancestor resampling. But the proposal itself is not necessarily very performant. And the reason why is, yeah, it's hard to choose a distribution for the ending point. I mean, you could run something else on the side to kind of come up with, I don't know, KD or something of it, but that kind of defeats the point because we're defining a proposal. So I would say if you have the option, I would say go with the forward.
And when you say more or less performance, is that in terms of the sampling diagnostics or the convergence rates?
So what I looked at in some experiments I did was I did repeated runs of the estimators of the normalizing constant in, for example, particle filters. So it's a bit empirical, to be honest. It was a kind of empirical measure. But yeah, if you have a look at the paper, I have basically different noise regimes. And then I compare how the mean absolute error of the estimator for the forward and backward change. Cool. Thank you. Yep.
I probably haven't asked you that because I same question before. I apologize, but maybe something's come up in the meanwhile.
Okay.
When you say hypo-elliptic, I suspect you have a system in mind where, say, the first component is always smooth, not influenced directly by round motion, the second component is always influenced by round motion. Right?
Yes.
Is there something more interesting where, like, the forward system starts to change and rotate function state space?
Yeah, so it's interesting. So there's actually so we use these diffusion bridge proposals for hypo-elliptic diffusions. And when they're actually defining, okay, what classes of hypo-elliptic diffusion do these things actually work on, i.e. for which we have a continuous time likelihood, they kind of sell this idea of the integrated diffusion, i.e. this thing you just described, which is, okay, in one component you just have, something which is interacting with Brownian noise, and in the other one you have something smooth. I will go briefly back to this, where is it? Drum roll. Yes, I will go back to this model briefly. So what we've actually done here, so I mentioned that in order to have the diffusion bridge proposal, in order to have this continuous time likelihood, we need this class of integrated diffusions. So I kind of have missed out a little detail here, which is that this process is not actually this process. We've actually applied Ito's formula. So we apply Ito's formula so that we put it in the form of an integrated diffusion. And we say that x2 tilde is this thing, so that it becomes an integrated diffusion, basically. So we use that transform so that we could guarantee that we have this continuous time likelihood result. However, in the paper of Van der Molen and Jorgis Birkins, Frank van der Molen, Maurice Schauer. So in their paper where they developed these bridge proposals for hypo-elliptic diffusions, they do a bit of a test drive on this model without doing the transform, which doesn't technically sit within the class for which the continuous time likelihood is defined. And they get the stuff that looks like it works, basically. So they go outside the conditions under which they proved its existence. Yep.
What are the upsides, downsides for working with this kind of continuous discrete state space model as opposed to being continuous, both signal and observation, or discrete in both?
Okay, so I'm not as sure about continuous in both, but I can answer discrete in both. So people tend to use, and it basically boils down to this low frequency thing. So if we have a regular state space model, the way these tend to be constructed oftentimes, so for example, in say a target tracking application, is okay, so a target tracking application would involve something's evolving as some kind of dynamical system, it obeys Newtonian dynamics. So we think actually this is our kind of first stab at what the model looks like. And then the state space model is actually recovered from doing some kind of Euler-Maruyama or some kind of numerical scheme discretization in between the observation times. But the issue with that is that significant bias is introduced into the model if we have a situation where we have low frequency. So I think the big sell for using this model as opposed to something simpler where inference is easier is when you have a situation like this, and also when you're really sure that this is the model, if it makes sense. So it could be some kind of biological process where you know that they obey ordinary differential equations of a certain form, and you want to evaluate uncertainty quantification in that context.
Yeah, so I was just curious, this example, if you instead had a stochastic fixing agreement, right, where on the X1 process you just introduced a small amount of Brownian noise,
yep,
then we would have something elliptic, right?
Yep.
And so, of course, maybe you're slightly misspecifying the process if you know that that's the answer. But have you thought about how this would change? Because then we'll be able to calculate this.
So if we were to use the forward.
Yeah, exactly.
Yeah, it's interesting. I have seen both formulations around in the literature. So some people work with the hypo-elliptic form, and some people work with the elliptic form. When people write papers about inference and hypo-elliptic SDEs, they do tend to turn to this guy quite a lot. So maybe in a similar vein, I kind of followed this path in the sense that so we defined this backward thing that only works for the hypo-elliptic diffusion, and then we used it as an example to show that, oh yeah, this works on this particular hypo-elliptic diffusion. But yeah, in terms of the model misspecification thing, I guess this is one particular example, but there are plenty of SDEs out there where, I guess, for example, one where you're modeling, say, you've got some velocity, and then, the displacement is then naturally the integral of that, where you can be pretty sure that hypo-elliptic is the right choice on that basis. Is that half answer?
Just because this one, like, somehow then the observation process, you're adding noise. Yeah, there's some noise from this, right? So you can sort of see a slightly different setup where some of the noise is coming in the true process.
I see what you mean. Yeah. So as in, is it necessarily the case that we have some smooth process?
With the yeah, exactly. Smooth process and all the noise is on the observation, or if you have a slight bit of stochasticity, a bit more stochasticity in the true process and a bit less in the observation process.
Yeah, I see. So it's about kind of identifiability of what's actually going on.
Or just maybe like a slight amount of misspecification is tolerable if it makes the inference easier.
Yeah. It's interesting. Yeah. Thanks. Yeah, of course.
So let's think what you're going to get is you refine the time discretization is that a very small amount of noise that you wish to add to the smooth component compensates a huge amount of noise to the second component. And if you allow that small amount of noise to the first component, that may bias your estimate of any coupling parameters between the two equations. Anything that couples the two drifts together. So here we have a 1 over epsilon there that sort of couples x2 to x1. you might get that drastically wrong if you allow the first equation to have a independent random noise. Like it's basically, if you just compare that noise, hypo-elliptic noise matrix to a Euler-Mariano instead, or something higher order, then that makes still conditioned with condition of a exploded self t tends to 0. And that's what leverages a little bit of noise in the first component and a huge impact in the second.
You're talking about a high frequency or a low frequency?
So I'm talking what happens to your Euler method as it works, some higher order method as you refine that to.
Yes, as you make it smaller.
Yeah. And if it's hypo-elliptic, then your conditional will explode. And that's essentially why a small bit of extra noise in the first component is equivalent to huge amount of extra noise in the second.
Because of the asylum,
Yeah.
multi.
Yeah, and yeah. So if you allow that extra bit of noise, then you might not force the epsilon to be estimated correctly.
Hugo on Zoom, and thanks for the talk. Did you try high dimensional sighting in your numerical experiments? I want to know how the computationals cause the scales with D in general.
Okay. I mean, the short answer is no, basically. Like we haven't tried it. Yeah, so I think as one thing I can comment on in terms of how dimensionality would affect this problem is, okay, so as we increase dimension and we're thinking about what it means to be low frequency, i.e. settings in which we need to introduce this particular class of model, what we'll find is that, you know, we have this this cursor dimensionality, concentration of measure stuff, and what I think that will mean is that the value of delta t for which we need to introduce this kind of setup in order to avoid introducing discretization bias, basically the value of this, if we to come up with some threshold above which we consider it to be low frequency, I think that this would decrease basically as dimension increases. But in terms of the compute cost, so then in terms of the compute cost, it might be the case that there might be some case where you would originally have some kind of discretization level, where, so with Yuka's work, he might be more comfortable working in the high frequency in this point. But then if the dimensionality of the process increases, but the discretization step size stays the same, then it might get to a point where you need to start thinking, oh, okay, now I need to start working in the low frequency in order to avoid introducing discretization bias. But yeah, I'll think about it. We should discuss this. We should discuss that, yeah.
Very quickly, another question on Zoom asking by Baptiste. Is it possible to estimate the parameters theta and how expensive it is, if possible?
Yeah, okay. So, yeah, good question. So I kind of indicated the possibility of inference on the parameter without actually discussing it directly, because it's not really, I guess it's not really the thrust of the ancestor resampling stuff. So this iterated conditional sequential Monte Carlo algorithm that I implemented in the numerical experiments, it actually has a natural extension, and the natural extension is called particle Gibbs, which some of you who are familiar with that literature may have heard of. And our path transformations, actually, I didn't really discuss it, but there's this classical Robertson-Strammer issue where if we try and update the parameter of a diffusion, given the latent signal, then this is actually a degenerate update in continuous time if we have parameters in the diffusion coefficient, because we can just access the diffusion coefficient through evaluation of the quadratic variation. So this is a problem with sample updates of the parameter given the signal in a Gibbs-type fashion. But actually, these path transforms we developed actually simultaneously solve this problem as well. And there's a bit in the appendix of the paper basically where I discuss that. But we didn't actually implement it, but it is theoretically possible. Yes.
Thanks again, Chris. Next PG seminar, which is in 2 weeks, would be given by an external speaker introduced by you, Anna. So please do look out for the email, and hope to see you there. Thank you.